All right, hello everyone. Thank you for making it to this presentation. Thank you for that introduction, Mike. Luckily, I don't have to spend much time talking about myself, and I can just move right into the topic at hand. So today we're going to talk about ultraviolet radiation, and that is a type of electromagnetic radiation. What I've put in this slide is the whole spectrum of electromagnetic radiation. So we'll refer to types of electromagnetic radiation by their wavelength and also by these general regions depicted here. So you can probably recognize regions like X-rays, visible light is what we can see, radio waves at the other end of the spectrum. And the characteristic feature of these waves is that a wave can be thought of with a fundamental particle of a photon, and that photon is going to have a wavelength. So the wavelength is also going to be associated with an energy. So depending on that energy or wavelength, that will dictate how that photon will interact with materials. So to kind of dive deeper into ultraviolet radiation, it's divided into a few different regions, depending on the wavelength. So starting with the highest energy, the lowest wavelength, from 100 nanometers to 280 nanometers is what we call UVC. Now, a subset of UVC is called vacuum UV, and that's from 100 to 200 nanometers. And that's called vacuum UV because the gases around us that we breathe, oxygen, nitrogen, are very absorbing to these wavelengths. So these wavelengths can't transmit through air very easily. Progressing on to longer wavelengths, such as from 280 to 315 or 315 to 400, those are classified as UVB or UVA respectively. UVB is typically thought, an easy way to remember UVB is that it's associated with burns, B for burns, and UVA is associated with aging effects. So these wavelengths of light from the UV and even extending somewhat into the visible range interact with biological materials and can cause molecular damage. So they don't have adequate energy to ionize an atom, but they do have enough energy to damage a molecule. And UVB and UVC wavelengths, which are the most energetic of the ultraviolet, they have enough energy to damage DNA or RNA. So how do these photons damage DNA or RNA? So the primary path is through what's called a DNA lesion. The incoming photon, pictured here, will interact with the DNA double helix. That will break molecular bonds and will reshape the DNA. It will cause it to reform, and that will change how that DNA is able to operate because it will now be damaged and won't have its natural structure. This same kind of damage can occur within human cells or bacteria or even in viruses. So what happens when these DNA lesions occur? A DNA lesion can ultimately disrupt the operation of the cell or the virus that where that DNA or RNA is located. When it disrupts the DNA, these DNA lesions ultimately lead to inhibitions in transcription or replication, and that basically means that the operation of the cell is not normal. When these photons enter a cell, for example, they can cause many DNA lesions, not just one. Like there's many photons, and that can cause many DNA lesions. Usually these DNA lesions can be repaired because cells have internal structures that can repair these DNA lesions. But the more damage that occurs, more DNA lesions, there's a smaller chance that they will all be repaired. So if a DNA lesion is not repaired, that can lead to a death of a cell, or it can lead to a mutation or possibly a cancer. Just some terminology. When we say that that when this effect happens on a bacteria, we can say that it can kill a bacteria, but for a virus is not living, so we'll say that it will inactivate a virus. And I forgot to mention something at the beginning. On every one of these slides, I've placed the slide number in the bottom left corner. So if you have any questions along the way, you might want to note that in the question, so that way it's easy to refer back. So each wavelength is going to have a different interaction with materials. So just to give an example is how each wavelength will interact with our skin. So a model of our dermis and epidermis is on the left side of this slide. Starting with the outermost layer of the epidermis, which is called the stratum corneum, that's at the top. And then we progress through the epidermis, and below that is the dermis. Depending on the wavelength of light, they will penetrate different depths into skin. So UVA is going to penetrate the furthest. Luckily, UVA it does not directly damage DNA, so we don't have to worry about it as being much of a hazard. UVB can penetrate far enough that it can get through the epidermis and even into the dermis. And that's significant because below this model shows that at the bottom edge of the epidermis, which is near the bottom of this model, is the stratum basal. And these basal cells are dividing. So if DNA damage can occur with where cells are dividing, there's a greater chance that these can lead to cancers. So UVB is going to be the most dangerous to form cancers. UVC, on the other hand, is not going to penetrate very far at all. It will penetrate maybe through the stratum corneum and then just into the top few layers of the epidermis. So not as dangerous in terms of cancer, but still these can, they are molecularly damaging, so they can cause DNA damage to the cells at the further out on the skin. Natural sources of ultraviolet light, the primary one is, of course, the sun. So shown in the spectrum here. So throughout this talk, I'll talk about the spectrum. And usually along the x-axis, along the bottom, is going to be the wavelength. And here that extends from 200, which is the bottom edge of the UVC. That's not the vacuum UVC. And this extends all the way up through the rest of the ultraviolet, the visible light, and then into the infrared region. Now, outside the atmosphere, there's significant amounts of light, signified by the height of each of these wavelengths. There's significant amounts of visible light, of course, that we can see from the sun. And then good amounts of UV, and even UV all the way down to through the UVC. However, by the time that radiation makes it through the atmosphere, it's filtered out because of products in our atmosphere like ozone. So the ozone layer is going to interact, or the radiation will interact with the ozone layer, and will actually absorb much of the energies in that range. So because of the ozone layer, we don't have any UVC radiation reaching us here at the surface of the Earth. We do have UVB and UVA, which is why we have to wear sunscreen. So the sun is a natural source for UV. It has been explored since the late 1800s and actually led to some of the first uses and explorations of UV for disinfection purposes. Originally, sunlight was used as a way to get UVB light, and it was observed that this could kill bacteria. Later in the 1800s, same kind of studies showed that this UV light in particular could cause sunburns. Early in the 1900s, applications kind of spread because new technology came out that was able to create UVC light artificially. Because of that, UVC was able to be applied in hospitals starting in the 1940s and 50s and was useful for preventing the spread of diseases like measles and tuberculosis. So these UVC sources are still available to us, but most of them are not used widely in the United States, but they are used to control the spread of tuberculosis in other countries. So the wavelength of UV light corresponds with how much it can, how effective it is at inactivating a microbe. So again, we'll talk about the range of UV light. This graph starts at 200 nanometers and only goes up to about 360 nanometers. So it covers most of UV. The key to this graph is this curve that starts low, goes up to about 100, and then drops back down in the UV at the edge of the A region. So this is how effective each of these wavelengths is at inactivating or killing a microbe. So the peak is at 265 to 270 nanometers. So after the studies found this peak, there's of course a search to try and find sources that could replicate or produce, artificially produce light in these ranges that correspond with with where the wavelength of light is most effective against microbes. So some of the common UV sources, one of them is mercury lamps. So that's the spectrum. Two of the different spectrums are shown here. A low pressure mercury lamp has almost all of its emission at 254 nanometers. And then a medium pressure mercury lamp has emissions that range throughout the UVC and UVB, but largely in the UVB and UVC region. Another source is xenon lamps. Xenon lamps have a much broader range of emissions. They go all the way from the UVC through the visible and through much of the infrared. And then another source is LEDs. LEDs are now able to be purchased that emit in the UVA, UVB, or UVC regions. So these different sources, now that we have different germicidal sources, can be used in a variety of media. The first one is water disinfection. This is commonly applied throughout the country. Water is flown past a UV light, and that UV light will inactivate or kill the microbes that are within the water. Besides water, it's also used for surface disinfection. In the bottom left is a picture of a New York City subway car. And there are a couple of xenon lamps that are set up to irradiate the space and expose all the surfaces within that car. This is also commonly used in hospitals, such as in the top right, where an operating room is used. And lights will be used, UV lights will be turned on in between uses of the room. The same thing with a mobile robot. Might go into the space, irradiate the space, and disinfect the surfaces. UV is also used to disinfect air. Two applications of that are in upper air. This is where the top portion of the room is irradiated with light that might be placed along the wall. So you can see them within this facility. They've been installed near the top of the wall. These lights project the light out and maintain that and have special features in construction that make sure that the light is only irradiating the top portion of the room above where anyone would be standing in the room. So any airborne virus or bacteria would be exposed to light in this region and could be affected. Another method of air inactivation is through heating, ventilation, and air conditioning systems, where ultraviolet lights will be installed in the ducts, so there's no danger of human exposure, and air will flow past the lights, and that air will be disinfected. So key to the use of ultraviolet light is measuring the ultraviolet light. We need to know a few factors with it. The most important is the spectrum. I've talked constantly about how the wavelength is going to determine how that photon interacts with biological material, how effective it is. So we need to know the spectrum. So that is the wavelength of light. The other key parameter is the dose. So that is how much light we are applying to a surface, for example. That is expressed in units of joules per centimeter squared or millijoules per centimeter squared. So the dose is simply the product of the dose rate times the exposure time. So how is efficacy expressed? So efficacy is the dose needed to kill or inactivate a portion of microbes. So on the graph to the left, we see increasing dose, starting with 0, progressing up to 1/2, 1, 1.5, and 2 millijoules per centimeter squared. And with increasing dose, we see a decrease in survival. So on the y-axis, we start with 1, which is 100% survival at 0 dose. And then as we apply more dose, we see a smaller and smaller fraction of survival. So we'll sometimes refer to this as a log reduction, which is explained here. A 1 log reduction, it means a 90% reduction in the viable microbes. 2 logs, 99, or 3 logs, this one's commonly used, is 99.9% reduction. So that means that a fractional survival is 1 in 1,000 microbes will survive. Important to dose is the Bunsen-Roscoe law of photochemistry. Luckily, you don't have to remember that name, but what does matter is the law of reciprocity states that the dose is what matters, not the dose rate. So that means that as long as you're not delivering this dose within too short of a period of time, and when I say too short, I mean a small fraction of a second, like less than a millisecond even, or over too long of a period of time, so over multiple hours, over 8 hours, more than that amount of time, then this law of reciprocity doesn't really hold anymore. So there's other functions that will come into play that means that you might not see the same efficacy for a given rate or for a given dose if you change the time scale too much. So a quick example of reciprocity. Here's 3 different irradiance values, 1, 0.1, and 0.02, and 3 different exposure times, 10 seconds, 100 seconds, and 500 seconds. But they all give the same radiant exposure, the same dose. So we would expect all 3 of these exposure conditions to produce the same effect on a microbe. So to apply that to some real world situations, we'll talk about, okay, we've all seen handheld UV lights and we're curious, will these work? So the short answer is maybe. If they are actually emitting UVC is one of the most important parameters. Most of us don't have a spectrometer to evaluate what wavelengths are coming out of a device. So we largely rely on the manufacturer that it is actually emitting UVC light. Pictured here is a product that was pitched earlier this year that you would attach it to your phone and it would somehow change the light coming out of the flashlight on your phone into UVC that would destroy microbes. That's kind of baloney. There's not any UVC coming out of your light, coming out of your phone to begin with, so you can't just filter it out. So you do need to be careful of some scams out there. So if you are emitting UVC, then you need to make sure that you deliver an adequate dose. So if you recall, dose is the product of irradiance and exposure time. So if you see these wands, they're often advertised that you can just sweep it back and forth across an area. Well, if you're sweeping it back and forth, you're only covering one area for a very short amount of time. So unless you have a very intense source, a very high irradiance, you're not going to deliver enough dose to be effective. So a wand like that might be effective if you just hold it in place for a long enough amount of time. So unless you have the proper tools to really know how long you have to leave it in one place, it's questionable how well a product like that can work. But if you do have UVC coming out of the device and enough dose to work, then you might have to worry about safety. So UV has an effect on our skin. Two of the most common problems are erythema, which is a reddening of the skin, as in a sunburn, and carcinogenesis, which might lead to melanoma or carcinoma. The relative danger of each of these is, once again, wavelength dependent. So expressed on this graph, we'll start with the dashed line. So that's for erythema. Erythema has the greatest danger, shown on here, in between 250 and 300 nanometers. Once you get above 300 nanometers, the danger drops. And when you're into the UVA, there's very little danger at all. Conversely, non-melanoma skin cancers are shown with, the danger of that is shown with the dotted line. So there's a little bit of danger, thought to be in some parts of the UVC, but most of the danger is in the UVB. The reason for this is, once again, related to penetration. So if you'll recall, the UVB can penetrate to those basal cells at the bottom of the epidermis, and those are most prone to leading to carcinogenesis if they're molecularly damaged. The UVC is not going to penetrate very far, so the cancer risks are lower in those regions. So UV also affects our eyes. UV effects is, once again, going to depend on where it's absorbed. If you look at this, this slice through an eye, the cornea is on the left, so light would come in from the left. It would go through the lens, and then it would land on the retina. Visible light, of course, can make it through, no problem. UVA and UVB will make it through the cornea, but will be absorbed largely in the lens, which is why UVB can lead to cataract formation. And UVC will be entirely absorbed in the cornea. Both UVB and UVC, so some of the UVB will be absorbed in the cornea, as well as the UVC, but these can lead to an effect called photokeratitis. Photokeratitis is also known as welder's flash or snow blindness. This is like a sunburn on your cornea. It's itchy, causes some tearing, but it goes away within a day or two, and as your cornea is naturally replenished with new cells. The graph here shows how, with changing wavelength, the dose that it takes to cause a photokeratitis effect. So the smallest dose is where there's the most danger of photokeratitis. So most of the danger is between 240 to 300 nanometers. Safety regulations have been made by some governing bodies, such as the American Conference of Governmental and Industrial Hygienists. So they've taken all the research on safety data for both skin exposure and eye exposure, and they've compiled it into a set of recommendations. So that recommendation is shown on the graph pictured here. The higher the graph is, the solid line for a given wavelength, that means that it is the more dangerous it is. So the peak of danger is at 270 nanometers, and it drops off throughout the UVC, and then largely drops off from the UVB to the UVA. And this is primarily based on photokeratitis, because that is the most sensitive, the eyes are the most sensitive organ for UV. So if we look at the germicidal effectiveness curve and the safety hazard for humans, they have a peak pretty much at the same point, which is unfortunate, but that tells you why all these installations of UVC have constantly tried to avoid any direct human exposure. So they're either irradiating the top portion of the room or within the HVAC system or in areas that are completely enclosed, so there's no danger of human exposure. So what about the far-UVC? So if you'll notice, most of these graphs, they just kind of stop with the data in the far-UVC. Reason for that is that there's no natural source for observing UVC. It's all filtered out from the ozone layer, so we don't have good data on what it does to humans, for example. And there aren't a lot of artificial sources in this region either. So a number of years ago, members of our lab came up with the idea to look at the far-UVC, specifically to see how well it could inactivate or kill microbes, thinking that it might have increased safety because of the properties of how it interacts with biological materials, specifically that it is highly absorbed by proteins. Because it is so highly absorbed, then it can only penetrate a few micrometers into biological material. And we're going to define this as 200 to about 230 nanometers. So as you can see on the graph here, starting with 200, it goes all the way to 300. The higher this graph is, that means that it's more highly absorbed. So the UVC, most of the UVB and the upper UVC is not very highly absorbed compared to the far UVC. So what does that mean? That means that size matters. So this infographic, if you start on the right, you can see the size of a human hair at about 100 microns. If you go down smaller, you get to a white blood cell, 25 microns, or a red blood cell, 7 to 8 microns. So if we can only penetrate a couple of microns with UVC, there's not as much of a danger as of getting into the white blood cells and the red blood cells or any other cell in your body. However, if you look at the bacterium, these blue rods, or even a coronavirus down here, they're so much smaller that there's no problem for these wavelengths to penetrate into those structures. So to illustrate this on skin, any far-UVC light that hits the skin surface is going to largely be absorbed in the stratum corneum. That's the outer layer. Same thing with the eye. Much of the tear film has proteins in it, and those proteins will be so highly absorbing that much of the far-UVC won't even make it to the outside of your cornea. And then to consider this on the cellular level, you can look at what's pictured here, a human skin cell, compared to the size of a virus or bacteria. The far-UVC can penetrate a virus or bacteria without an issue, but it won't penetrate very far into a skin cell, and it won't penetrate to where the DNA is in the center of that cell. So now we need a source of far-UVC. So maybe 20 years ago, research into excimer lamps really progressed. And a couple of key excimer lamps were created that use different gas mixtures. One of them was krypton chlorine, which principally emits at 222 nanometers, and krypton bromine that principally emits at 207. So an example of this is the krypton chlorine spectrum here. So once again, wavelengths starting at 200, going up to 300, and almost all the emissions are at 222. The red line depicts where that gas mixture emits, and you'll notice that there is some emission going up into the rest of the UVC, all the way up to about 260 nanometers. So we already know that those other UVC wavelengths are particularly hazardous. So we use a filter with these krypton chlorine lamps to remove those other UVC emissions outside of the primary peak at 222. So now we need to know, since we have these lamps, does it work? And we ask, is it safe and is it effective? So what we know about safety, we know the biophysics. I went over this, how we know that with the limited penetration, UVC already, that didn't make it very far into the epidermis. And with the added absorption in the far UVC, it's going to make it only going to go even shallower. So it will barely make it to the stratum corneum. What else do we know? We know the existing limits. So I discussed that on the left. We know that at 222 nanometers, those regulatory bodies have already deemed it safe for repeated exposures for 23 millijoules per centimeter squared every day for 222 nanometer light. And then safety studies. So we have done a number of safety studies here, especially in our lab at Nevis Labs. We've started with artificial skin models. So an example of the skin models in the upper left of these four. So it has the same key features. It has a stratum corneum, an epidermis, and a dermis. So these are histological sections. The unexposed picture is in the top right. I've added a red line to indicate where the stratum corneum is. If you're not used to looking at these, it can be difficult. And then exposing to different doses of either 222 nanometer light or 254 nanometer light. We chose doses that are equal to the daily exposure limit, and you can see the effects. The key here is that we were staining, which means that we look for evidence of DNA damage. And in this instance, we were specifically looking at CPDs. So if you recall, a photon will come in and alter the DNA, and we're able to mark cells that have that kind of damage. So at the exposure limit right now, 6 millijoules of 254 nanometer light causes damage in the epidermis. So you can see that in the black cells along the surface. Whereas for 222 nanometer light, there's no damage present. That's a really good sign. Knowing that, we went to even higher doses. So this is two graphs, once again showing CPDs. So a higher number of CPDs on the graph means more damage. And the other DNA lesion that we looked at was 6,4 pp's. So we looked at two different types of lamps again. We looked at a far-UVC lamp, which is the blue dots, and we looked at a conventional 254 nanometer germicidal lamp. So with increasing doses, even up to 150 millijoules, so this is 6 times the current limit, we didn't really see any CPD production or 6,4 pp's. Whereas those same doses of 254 nanometer light showed significant damage. We've been extending these tests to mouse skin. We have a current study that's just now almost done. It started last summer, and we've been exposing mice, cohorts of mice, to different doses ranging from 100 millijoules per centimeter squared up to 500 millijoules per centimeter squared. We expose them 8 hours a day, 5 days a week, and we've been examining the skin. We haven't seen any tumors or any abnormalities during this time. And we're going to continue analysis to look at deeper evidence of damage once the 60 weeks is over. We've also been doing tests on mouse size. We give a mouse the same kind of eye exam that you might get if you go to the eye doctor. We'll look at the mouse eye through a microscope, and we'll examine the different different anatomical pieces of the eye, from the cornea to the iris to the lens, et cetera. And we'll look for evidence of damage. And we haven't seen any UV-related pathology, so no UV damage. Other groups have also joined us in this expedition to explore how far-UVC is going to affect our health. And they've all shown similar results. They've shown that far-UVC is unlikely to cause skin damage, and it's not causing significant eye damage either. So does that mean that it changes to the safety guidelines are in order? Does that mean that higher doses might actually be safe? And that's something that still needs to be explored. These limits have been established for a few decades now, and lots of evidence is required to change them. But there's still a lot of room to work within these regulatory limits. So now that we have a lot of evidence about it being safe, we need to know if it's effective. So we originally started this work looking at methicillin-resistant Staphylococcus aureus. That is an antibiotic-resistant bacteria, common for hospital-acquired infections. And we looked at the ability of increasing doses of UV light to inactivate or to kill these bacteria. And we compared the 254 nanometer light with 222 nanometer far-UVC light. And we see about the same efficacy in killing, which is really good news. Moving on to airborne viruses, which is, of course, applicable to the current COVID-19 pandemic. You have to think about how these viruses are transmitting from person to person throughout a space. So whenever we sneeze, cough, talk, we're expelling tiny droplets. These droplets are going to range in size from, some sneeze droplets are hundreds of microns in size, and that you might be able to see those droplets. A lot of droplets, though, are very small. We're talking 1 or 2 microns in diameter or smaller. These droplets you're not going to be able to see, and depending on the size of these droplets, they will be suspended in air for different amounts of time. So, for example, a large droplet might only hang in air for a few seconds. It might fall to the ground pretty quick. A droplet that's only 1 or 2 microns in diameter is going to hang in the air for hours, tens of hours even, almost indefinitely. So depicted along the bottom is some results from other groups. They simulated this. They had a person depicted here in the top bottom left, and what happened if they expelled a particle of a different size. If it was a large particle, it just kind of dropped to the ground. As the particles got smaller and smaller, 1200, 100, 10, less than 1, these particles would stay suspended and move around in the air a lot. That means that if they're suspended, that means that other people can breathe them in and possibly get infected. But since they are in the air, that means that that we have lots of time to inactivate them. So we started testing the ability of far-UVC to inactivate an airborne virus. So we created an artificial environment where we would aerosolize the virus. We'd put it in a nebulizer over here to the left. The aerosol would move through this container. It would be exposed to far-UVC light in the center, and then we would collect the virus. So we started this testing with influenza, and we found that it was very effective against influenza with a 1.6 millijoule per centimeter squared dose. It was able to inactivate 95% of airborne influenza. And considering that the safe exposure limit is 23 millijoules, that means that you could do this 95% inactivation almost 15 times a day safely without any issue. We recently extended that work to coronaviruses. For this work, we used what's called a surrogate for SARS CoV-2. So because of the, of course, hazards of working with SARS CoV-2 right now, we used a surrogate, which means that it's also a coronavirus, but it's of a different variety. So we use ones that are commonly available. Many of us are exposed to them regularly, and they cause the common cold, but they're far less hazardous than SARS CoV-2. So we used our same aerosol exposure setup, and we looked at the dose response and the fractional survival. So with about 1.5 millijoules, we're easily getting 99.9% inactivation of these coronaviruses. So that's a very small dose. And based on the daily exposure limit of about 23 millijoules per centimeter squared, we came to the conclusion that we could inactivate 99.9% of airborne coronavirus in about 25 minutes using the recommended exposure limit. And even though we looked at surrogates, I just wanted to point out that other works have shown that 222 light, which we used on a surrogate, is effective at disinfecting SARS-CoV-2. It wasn't in an airborne environment, but everything points to this also being effective on SARS-CoV-2. So what are good applications of far-UVC? We see hospitals, schools, public transport, anywhere that there's an indoor area where people are gathered close together. And the huge advantage of far-UVC is that it can safely irradiate directly onto areas where people are present. So instead of only irradiating the top of the room, we can shine those lights down, and that means they're more effective because we're actually radiating the volume where people are at. So we're radiating where people are breathing out and where much of the air is in the room. So there's more air to disinfect. And the added advantage about radiating directly down is that you're also decontaminating any surface that far-UVC light lands on. Knowing that, there are some applications where other forms of UV light, like the traditional UVC, maybe with germicidal lamps, mercury lamps, that are more dangerous, where those are still very effective. So anytime that there's no people around, it's still effective to use other types of germicidal lamps. And there's are advantages because other types of germicidal lamps are less costly and easier to obtain. So some of those upper air applications, I don't want to knock them. They're still great. They still have lots of value. So if we're exposing people, we always have to worry, like, okay, how is this going to affect our microbiome? So the microbiome is what are the microbes that are living on our skin, within our biofluids. They might be in our GI tract. So we don't want to disrupt this too much because some of these microbes are actually helpful to us. So is constant radiation with far-UV light going to matter? And we don't really think so. We do a lot of things that are naturally going to disrupt the microbiome. We wash our hands regularly. We take regular showers. We go out in the sun. So there's UVB that's going to hit us on our skin, and that's going to have some antimicrobial effect too. And much of our body is shielded with clothing. So any far-UVC light is not going to penetrate through our clothing. And so most of your skin isn't going to be exposed. And to add to that, much of the microbiome is even deeper within the body, such as within the gastrointestinal tract, or even deeper within the skin. So this skin model shows that some of the microbes might be well into the dermis. And since we're not penetrating hardly past the surface, there's not a concern that we're just going to completely wipe out every microbe. Another worry is that we might be creating ozone. So some people are aware that ultraviolet lights are used to create ozone. So ultraviolet light that is less than 242 nanometers has the potential to interact with oxygen and create ozone species. This graph on the right shows the likelihood of that. And while it is possible at between 200 and 242 nanometers, it's highly unlikely. And that's the amount of ozone produced from far-UVC lighting is very small. And we've always tested this when we're using our lamps, and we've never read anything that's anywhere near a dangerous level. Future developments, we're working to demonstrate the efficacy of these lamps within spaces such as within a hospital. And we're also looking to find out more information about the specific wavelength risks in the far-UVC. So to really analyze what is happening in between 200 and about 240 nanometers where there wasn't much data before, because this can really guide the development of more better sources and filtering requirements. So the next step with far-UVC is that we need more sources. If you try and purchase one of a far-UVC lamp right now, you're not going to find many people that are making them. There's not a lot of options. So while the people that do have the capabilities to manufacture these lamps are doing their best to scale up, this is not a common technology, so more manufacturing will be welcomed. And similarly, filter technology is also expensive and new filters are needed. A lot of people wonder, what about LEDs? We've kind of gotten used to being able to just buy an LED at whatever wavelength we require. Unfortunately, that's not the case in the UV. About the lowest wavelength LED that you can purchase right now is about 250 nanometers. So anything in the far-UVC is purely experimental and not really available. So we hope that LED technology will continue to progress and make shorter wavelength LEDs available. And along with new sources, we need more research on safety guidelines, what we've talked about, and to really figure out what the safe operating limits are, so that the higher safety limit, that means that your far-UVC is going to be more effective because you can apply more dose. And then one of the last things, and I thank you all for coming and viewing this talk today, is that public education is important. We've kind of been taught that all UV exposure is dangerous and we need to minimize it. I think changing public's perception of UV and realizing that this might be a worthwhile risk to take, a small amount that is found to not cause a health hazard, but can show a great benefit, might be a risk that is worth exploring. If the choice is between a small amount of UV light constantly around you that scientists have shown is not dangerous, and on the other hand, catching COVID-19, I think many of us would take the risk with the UV light. So I want to thank the research team behind this. Dr. David Brenner leads this effort. Dr. Brenner and Dr. Gerhard Randers Pearson were the original, they came up with this idea a number of years ago. And then Dr. Panaya, Dr. Bonanno, and Dr. Kleiman have done a lot of the work in the past 5 to 10 years that this has happened. So thank you very much for your attention. And